What if a single open model could see, listen, read, and reason, and run entirely on the graphics card sitting under your desk? That's Gemma 412B Unified, released by Google DeepMind under the Apache 2 license. In this video, we'll unpack how it works, install it from scratch, watch it handle real images and audio, and measure how fast it actually runs on a consumer GPU. Let's start with the big idea. Gemma 4 is not just another text model. It's a rethink of how multimodal models are built, aimed squarely at local deployment. Gemma 412B Unified accepts text, images, audio, and even video as input, and produces text as output. It handles a context window of up to 256,000 tokens, enough for entire codebases or hours of transcripts. There's a built-in thinking mode, where the model reasons step by step in a hidden channel before answering, and it was pre-trained on more than 140 languages, all under the permissive Apache 2 license. Here's what makes the unified variant special. Traditional multimodal models bolt separate vision and audio encoders onto a language model. Gemma 412B eliminates those encoders entirely. Raw image patches and raw audio waveforms are projected straight into the embedding space through lightweight linear projections. Everything then flows through one decoder-only transformer. The payoff is lower multimodal latency, and the whole model can be fine-tuned in a single pass. The family comes in 5 sizes. E2B and E4B are designed for phones and laptops, using per-layer embeddings to stay tiny. The 12B Unified, our star today, targets consumer GPUs. The 26B A4B is a mixture of experts' design that activates just 4 billion parameters at a time, so it runs nearly as fast as a small model. And the 31B dense model sits at the top for maximum capability. Time to get our hands dirty. Chapter 2. Installing Gemma 4 on a Linux workstation with an RTX 4090 with a clean, reproducible toolchain. First, reproducibility. We use asdf to pin Python 3.1.8 and of 0.8.88 locally for this project, so the exact toolchain is recorded in a .toolversions file. Then it creates the virtual environment in a fraction of a second. One important habit. We point the Hugging Face Home variable at a dedicated cache on the large data drive, so 24 gigabytes of weights never clutter the system disk. Next, the GPU stack. Modern PyTorch wheels ship with the Qday runtime bundled, so a plain install just works on the 4090. The crucial pin is Transformers 5.10.1, the very first release that knows about the Gemma 4 unified architecture. We add bits and bytes for quantization, Gradio for the demo interface, and Librosa for audio. Finally, the adf download command pulls all 24 gigabytes of weights into our shared cache. Here's the loading code, and it contains the one real gotcha. The model is 24 gigabytes in BrainFloat 16, exactly the size of our GPU, so we quantize it to 4-bit NF4 with bits and bytes. But notice the skip modules line. The encoder-free vision and audio projections consume raw pixel and waveform values, and if bits and bytes quantizes them, image inference crashes with a cryptic layer norm error. Keep them in BF16, map everything to GPU 0, and you're in business. The result is dramatic. 24 gigabytes of weights compressed down to just 7.7 gigabytes of VRAM with NF4 quantization. The model loads in under 10 seconds from a warm cache. Everything stays 100% on GPU, no slow CPU offloading. And with 16 gigabytes of headroom left, there's plenty of room for the KV cache, even on very long conversations. Chapter 3. Enough theory. Let's watch the model work live through a Gradio interface, with real screenshots of inputs and outputs captured on this exact machine. This is the demo API, a Gradio web UI served on localhost port 7860. You can attach images, audio files, or video, or records straight from the microphone. Responses stream in token by token, and a settings panel exposes a thinking toggle, the system prompt, and sampling controls. There's even a programmatic API, so the same model can power automation scripts. First use case: image understanding. We upload a photo and simply ask a question. Given this picture in the question, "What bridge is this?" the model answers Golden Gate Bridge correctly in about a second. The same pathway reads documents, parses charts, understands UI screens, and even deciphers handwriting, all without a dedicated vision encoder. Second use case: audio. We hand the model a WV recording. The raw waveform goes straight into the transformer. It transcribes the speech accurately, entirely on device. Nothing ever leaves the machine. And beyond transcription, the same audio pathway performs speech translation across major languages. Third use case: thinking mode. Flip the toggle and the model reasons in a hidden thought channel before committing to an answer. Asked what 48 times 27 is, it works the problem 4 different ways. Long multiplication, the distributive property, rounding tricks, checks that they all agree, and only then answers 1296. The interface folds the reasoning into a collapsible block you can inspect. So how good is it really? On Google's reported benchmarks, the 12B Unified scores 77.2% on MMLU Pro, 77.5% on the AIM 2026 Math Olympiad with no tools, 72% on LiveCodeBench, 78.8% on GPPU8A Diamond, and nearly 80% on Math-Cheat Vision. Numbers that beat last year's 27 billion parameter Gemma 3. And on this actual machine, the model loads in 9.44 seconds, sits at 7.7 gigabytes of VRAM, and streams 19 to 24 tokens per second, 4-bit, fully local, at 0 cost per token. And that's Gemma 412B Unified, frontier-level multimodal AI that sees, listens, and reasons, running comfortably on a single consumer GPU. All the model weights are open under Apache 2. Available on Hugging Face at Google/Gemma 412B. Everything you saw, the demo, the benchmarks, and this very video, was produced on one RTX 4090. Thanks for watching.